for the normalization operator. And of course, so essential set of uniqueness, this means essentially this equation has no solution for any t. So set S. So for any t, this implies t to the 0. Because if there is a solution, you cannot put it in the normal space. This means this term can be eaten up. So this means there is no solution. So any element here, you cannot solve this equation. If you can solve it, it's in the complement, in the range. So the second thing I want to say a few words. The second thing I want to make up is that so about the classification for spheric CR manifolds. So this is one of the very important problems in several complex variables. So many years ago, G and I proved the theorem, and later, when I wrote a survey paper for Gong's 75 process, it generalized a little bit. And in that setting, we know that so if M is like embeddable CR manifolds. So embeddable, so this is the embeddable CR manifold. So this means you can put it in sequence N. So for people like us, who only working on several complex variables, we always consider embeddable. So it's already somewhere, so in CN, we say M is algebraic. It's a very important notion in SCE. So this means there is embedding. There is embedding. Well, this is defined by polynomials. And it's a very important class of CR manifolds normally. And when there is a result, so here's the theorem. So whereas the proof is more or less in my joint group with G in 98, so math research level. But it's based on my algebraic theorem before, okay? So the theorem says, if M is split plus algebraic, then so M has the whole function, type of 1. That's the whole function in character. The same dimension, just left dimension. Gamma is finite. And conversely, this part, this is known, okay? This is Kaplan. No, not any Kaplan, but Henry Kaplan. So Henry Kaplan proved that any finite group, there is a homogeneous realization. It's you can this is well known, okay? So now the only remaining question is to classify non-algebraic spheric CR manifold. But then so there's a list. So I mentioned if it bounds a variety, if it bounds Stein manifold, it's very hard. And if not bounds, then essentially it's from the ground too. So this is the conjecture people believe to be true.
Can you tell me what exactly spherical is? Can you recollect what spherical is?
Well, spherical means locally it's the same as sphere. Locally, it's holomorphic equivalent to sphere.
So, okay. In that case, suppose M is non-compact.
Oh no, we always consider compact.
No. But suppose M is non-compact.
M is then it's more
complicated. And algebraic. What can you say about it?
That I don't know. So you mean it could be anything, right? You could just take any kind of piece of sphere. You see algebraic, it's the same as sphere. Well, so I'm not going to go more. The many things I talked about, you can find in my homepage. My homepage. So this is except two lecture notes. I'm worried to put it there because there are some copyright issue. Okay. So homepage. So you go to Rappers, you find the X1 homepage. Okay. There are many things to relate to I discussed here, especially for the Chen-Moser wire tensor. So I mentioned Chen-Moser wire tensor for the strong pseudo-complex case. It's a very difficult tensor, but if you go to Levy-non-degenerate with passive signature, it's truly behave like a curvature tensor. And here you can do a lot of things, And I have several papers on this side, so you can look at that. But there are two lecture notes, similarly email sent to you, okay? PDF file. One is the Chima lecture note. This copyright finger, there's a copyright issue, So I'm worried to put it there, okay? And also there's for the Chen-Moser wire tensor, I write a very lengthy lecture notes and all connections with the differential mathematics. It's also since it's going to appear in some other publisher. Okay, so I cannot put it there. You send me an email, I'll be happy to send you a PDF file. For papers, I put it there. So now, so I skip chapter 4 actually. So I skipped chapter 4. geometric side of Cartesian model theory. I hope I can come back here, so I want to finish this as fast as possible. And then so I come back to chapter 4. Chapter 4 is my writing. So I can control my time, in some sense that, if I have more time, I do more. If I don't have less time, do less, okay? So now let's jump to directly chapter 5. Chapter 5 is for the geometry and the normal form theory for Bishop manifolds. For CR manifolds with so with CR singularity, so it's not CR, cannot be the boundary domain.
Which is this paper by Arika Khan?
Onhika Khan.
Yeah.
When I think what's long ago, 1945. Yeah, it's they call the sphinx space form, It's a realization. It's not actual. So you see, this is the same. So it's bound to what? So it's a boundary of Dn quotient gamma. It's what they call the quotient singularity.
Yeah.
Any quotient singularity can be autoralized. Yeah, that's what you
do.
Yeah. I think it should be in my Chima lecture notes. Okay. No, probably not in Chima lecture, but in another lecture notes, survey paper, where I read this question. So I think 43 or 45 by Erika, not Erika.
Not Erika.
Yeah. So not Erika. So now let's talk about. So I put in this form because I don't have to write a lot more. Okay. Otherwise, I cannot go too far. Okay. So first, let's define what a Bishop manifold is. So let's recall first. Okay. So here, let's just recall that. For example, any real surface. Now it's real dimension 2 in C2. We look at the hyperdimension. That's the chance you get CR manifold with CR singularity. Okay. And so for any point Q in M, now you can define this holomorphic in the vector space, as I mentioned before. Now its dimension, we call the Cauchy-Riemann dimension of M and P. And you can write it as a number, whatever it is. Let's just put it for simplicity, RQ. But in this setting, this Q could be only 0 and 1, cannot be 2, because it's dimension, Okay. So if Q, this function can only jump, cannot get slower. So this means if RQ equal to 0, then the nearby will also be 0. In that setting, so we say M is totally real. There is no complex structure at all. You are only doing real analysis of M. Okay. So the first time I heard about CR, I probably when I was at Wuhan, I think 94, 95, in Homendo, came to give a talk. He talked about CR. And he used a very, in Beijing, I forgot, not Wuhan, Beijing. And I went to Beijing, and he used a very, very, intuitive language. He said he did not call CR. He said, I'm doing 2 plus 1, 2 plus 1 complex real analysis. This means I do 2 complex analysis plus 1 real analysis. So that's called CR, okay? So this means you do complex analysis and the real analysis together. So now let's give you typical example of total real manifolds, okay? So for example, C2, you have a lot of plane, okay? If the plane is arranged like this, so you take the first, you take the real part from Z, take the imaginary from W, then this plane is totally real. Now, if RQ is identical to 1 near Q, then M is a Riemann surface. The simplest example of Riemann surface is just like a copy of C1 and C2. In this setting, you both X, Y from same Z. This is so these are 2 typical examples, okay, of 2 typical examples. Now, so the situation is that if at the point is 1, you have a complex tangent. It's touched by a complex line. But not identical 1 in the neighborhood Q. Then we say Q is a complex tangent point, or CR singular point. So we notice that M is not singular, but the structure is singular. And this is so the structure, the holomorphic structure is singular. Suppose Q is a CR singular point of M. Now, so because we look at the holomorphic property of M, you are always allowed to find the best holomorphic coordinates you can to simplify the manifolds. Okay. Now let's choose the holomorphic coordinates. We move Q to 0, and this is the complex line. Now we just say it's defined by Z-axis, defined by W equals 0. Okay. Now, so here the definition. So let's look at, in this setting, as I mentioned, the previous two sections are called CR setting. It's not interesting anymore here. Now, so the origin is called the non-degenerate CR singular point. If no matter how you make change of coordinates, so the order of contact ever with this is a complex tangent space cannot be more than 2. Cannot be more than 2. This means it touches only to the second order. We know this means in some sense means non-vanishing property of curvature. Okay. So then one can always find a new coordinate system in which m near q equals 0 is defined by this form. It's more or less like we find the lab before. It's exactly the same. This is a dual B-sharp, okay? So now, so the only different issue is that, so if you arrange lambda bigger than 0 and infinity, you know, so in the strong pseudo-convex case, you can always make lambda equal to 0, okay? But now you cannot do that anymore, okay? So this lambda already is a second order invariant. So we call the B-sharp invariant. So now it's an invariant. So it's invariant. So a real surface is called a B-sharp surface if it only has non-degenerate CR singular points. Either total real, but if you go to CR singular points, you only have CR singular points. Okay. So this lambda is the number which catch the geometry of the manifold. Let's give the picture. Okay. So give the picture. So it's a surface. You can draw the picture here. So this is lambda between 0 and 1 half. So this is a cylinder here. The model, so essentially, this is the model. This is lambda equal to 1 half. And this is the surface. It's a subtle surface. This is lambda equal to 1 half. So this is the picture we have in the geometry. So lambda, you see that the value of lambda, you know, make the geometry of M very different. Okay. Now, more generally, so you can look at a submanifold embedded in Cn, and we look at the critical dimension. You know, this critical dimension is a dimension you start from real analysis to complex analysis. So this is why people, you know, so always care about this dimension. And actually, this dimension, people find a lot of application outside of several complex variables. So it's called the B-sharp manifold if the generic point in M is either totally real or a CR single point, which is not, or a CR single point, you know, so which is non-degenerate in some sense, which I mean, so this is in a good coordinate system. Say now we are in Cn, a B-sharp manifold near CR single point can always be written in this normal form. This is a second order normal form. It's just like we define strong pseudo convex. Okay, but the lambda between 0 and infinity. And here, so this, you know, so how many equations we have? We have essentially m minus y equation. Here we have 2 equations. So this is y alpha. No, this is here we have m minus 2 equations. Here we have 1 complex equation, 2 real equations. Eventually we have exactly n real equations. So it defines an m manifold in Cn. So B-sharp manifold, especially B-sharp surfaces, are the most important example of non-CR manifolds. So the most important, okay, from any point of view, you know, you might consider. Okay. So this, let me say a few words. Okay, so B-sharp manifolds were first systematically studied by B-sharp in 1965. Okay, so this is one of the fundamental papers in the subject. You know, so he called this P an elliptic parabolic CR singular point in terms of the value of lambda. This is elliptic, this is the parabolic, and here this is hyperbolic. So the geometrical homomorphic structure depends strongly on the nature of lambda. Okay. So this is the manifold now I'd like to address in this chapter. Okay. So now I have to give you some motivation. So why do people care about B-sharp surfaces? Okay, there are many motivations. Okay. First is connection with something we call the complex plateau problem. You know, so we know when you solve degenerate Mongian-Betty equation, complex Mongian-Betty equation. So I don't know. So far, there's nobody who succeeded to get a regular solution by using estimates. The only solution you can get is using complex analysis, Fourier theory. And this is the first place we encounter this problem. I'm going to show you later. Okay. And you can use this sort to solve plateau problem and also plateau problem. Okay. So this is from geometric point of view. And the second point of view is that so It's a generic, essentially, also generic and the most important model of manifold with structural singularity in complex analysis. Structural singularity, okay? And so it's just very popular in the 80s and 90s of the work of Gromov because they are closely connected to the study of many problems in symplectic geometry. After the work of Gromov and Yakov Hofer and misspelling, okay? And other mathematicians. And Sarko actually showed me a paper in the Hofer first solved this Wenson conjecture by using elliptic Bishop surface. Okay, that's the manifold. Once you have like three surfaces, you always find the Bishop surface inside. Then you substitute something. You find the invariance inside. Okay, so so this is the later 80s. But actually, so Moser discovered even in the 70s, and so these are problems from the dynamic point of view, normal form point of view. They are similar to many problems in cells and mechanics. And including small divisor problem in classical dynamics. Here the work is Moser-Webster and Moser, etc. Okay, so this when you do normalization problem in in cells mechanics, okay, they are very similar to the normalization problem here. Not for CR, not for strong silicon convex. Okay, there's one thing I did not say. Okay, so there's one more. Okay. So I mentioned many times, okay, the Chen-Moser theory, why? The Chen-Moser theory is easier. Essentially, it's a linear decoupled normalization problem. You need only, it's a linear decoupled. So from the normalization normal point of view, it's trivial, essentially. Decoupled is a linear system, linear decoupled system. But so in the front row, but of course, there are many geometries, so that's make it very intrinsic, okay? Make it very difficult, okay? So, however, when you do Bishop surface, then it's going to be nonlinear undecoupled system. So that's why I make it extremely hard to attack. Nonlinear undecoupled. So that's the first example in SCV, well, when you do normalization, you have to handle these things. And actually, so you can model fundamental connection for this normalization with the problem in mechanics. Okay. So these are some part of the reasons we look at these Bishop surfaces. Now I tell you more motivation about the study of this these manifolds. Bishop surface, I would say, from the dynamic point of view, this is what people care. But from the geometric point of view, you want to look at Bishop manifolds. Now I'm going to explain to you why Bishop studied this problem. His motivation is not from all these are very modern terminology. Okay, his motivation is from the class complex analysis point of view. And then you find so here's what I'm going to focus now. Okay. So now in the classical complex analysis, you give a set and you want to find the holomorphic Hall. Just like you give a subset in Rn, you want to find the common stuff. It's very easy, you connect all line. But holomorphic Hall is very hard to find. So how do you define the Hall? You just take all, suppose this is closed, otherwise might be, suppose it's closed, okay? So you want to find all pseudo-convex subdomain which contains E, and then you take the union for omega. This is called holomorphic Hall. Okay? Just like you find that all convex domain containing E and took the union, that's a convex Hall. And you want to know how you describe these things, okay? So you also study the local holomorphic Hall. I only find the Hall of E near P. You can't by the ball and look the Hall here. Okay? And this is a fundamental problem in SCV. And even today, so this is like a level problem, it's all this type, okay? You give a subset in CN, you describe the holomorphic Hall or local holomorphic Hall of E near P. Okay? As you can imagine, it's one of the basic problems motivated the whole subject to develop. So in the very full generality, if we want to solve the problem in the very general setting, it's impossible. So you have to work on case by case. But anyhow, any problem related to these things is regarded as an important problem in classical complex analysis. Okay, just like in classical geometry, you want so this is the motivation of Bishop in the 1965. Okay. Now, So the above problem is very difficult in the general setting. Now, so we focus on the case of a critical dimension in CN. That's we shall look at it. So he said, let's look at so the first case you start, the complex analysis jumps in. Okay, that is the critical dimension case, which is generic, total real, and with only non-degenerate complex dimension. So these are something we call the B-sharp submanifolds, which I define. Okay. As I mentioned, so related to this problem, there is something we call the complex plateau problem. Now I'm going to tell you. Okay, so what is a complex plateau problem? So here is the basic problem. So that one, I'm not sure this is the basic problem. This is more geometric problem. Okay, you look at another problem. Okay, so you let M be a real half-dimensional manifold. You don't care what dimension. Okay, then you want to find you want to solve this question. Can you find a Levi-flat submanifold M hat? This means which has M as part of smooth boundary. Okay, and so Levi-flat means M hat is followed by a family of holomorphic disks now. Area there is foliation. The Levi form is equal to 0. Okay, and you want actually if you want to use this solution of this plateau problem to solve the classic problem I mentioned above, you want the disk shrinking down to 1 point, so that you can apply the continuity principle. For those who have knowledge about basic SCV, the continuity principle is the basic principle we study. We construct the whole. So this means
so the first picture you will do it by this analytic disk.
Yeah. So it's here it's always trivial.
Yeah. But
so
this one there will be.
I'm going to make this. Here is trivial, and here is unstable, so people then can ignore it. Here is trivial. So this is by Stahl, so for snapshots, these people. Okay. So let me say like this. So what is a continuity principle? Probably, so unfortunately, I don't have much time to explain. Okay. So here's the issue. Okay. So this is not convex. So why? Because I start from this line. I move this line all the way. Okay, move this line all the way. So let me move like this all the way. Okay, so at some point, my terminal point, will still stay interior, but my interior is going to touch the boundary. So this is not okay. So actually, this is if and only condition for domain to be convex. The same reason in several complex variables, so a domain has a trivial local holomorphic core is the same. So this is so you start from holomorphic core and you keep moving it, and so whenever your boundary stays inside, your interior can never touch the boundary. Then it's still convex. Okay, so that's why you want this to shrink down to shrink down to 1 point here. But then you can sample this disk to push it forward. So that's why you want this problem. Okay. So problem 1 and problem 2, and so in this special setting, so they are equivalent. So due to so-called what I've described by continuity principle and bounding tree. So suppose for example, you find a hole. If it has smooth structure, it has to be a Levi flat. Why? Because it cannot be still convex. If it's still convex, then you can fill in here. Still concave here, you can fill in here. So it has to be Levi flat. Okay.
There's also bubbling phenomenon.
Yeah.
Bubbling, because if you take this, then it go up like this, and then push it forward, there will be a
no, be careful. Yeah, it's like a maximum principle. Okay. So so this means so you cannot grow too high, then the boundary. The boundary control.
This can bubble and touch.
Yeah.
Inside.
Yeah. So this is the boundary trick. What I'm saying that pseudo-convex in here. So for example, this cannot be Levi flat. If this is the hole, this cannot be the case because you can still fill in this here, make it bigger. Okay. So these two are equivalent. Okay. Now there's one more question. Now this is more related to normal form. Okay. So there is a very special Levi flat submanifold. It's called standard Levi flat submanifold. It's essentially in our setting here. It's Rn class C. The complex structure is everywhere here. It's a subplane. It's a plane. Okay. There is only one complex structure here. Now, so when you do analysis here, it's one complex variable plus n real variable. That's what we call. Okay. Now, so if M is sitting inside H, so if M is sitting inside and if M is curved, then the domain M hat bounded by M is a Levi flat manifold we are looking for. For sure, it's also the whole. Okay. Actually, if you know M bounds a real analytic Levi-Flat manifolds M hat with M as part of its real analytic boundary, then there's a classic theorem we can count. Okay, so feature says M hat mu M can be a bipolymorph map to H. So hence, in the real analytic category, so the above problem is also equivalent to this problem. It's a flattening problem in real analytic category. So this means that M be a real analytic M plus 1 Bishop manifestation can M be locally holomorphically embedded into H. Holomorphic embedded, okay? So all these problems are equivalent in the real analytic category. But so these only are equivalent in the smooth category. So this is another thing I want to say. Okay. Now, so problem 2, since I know there are a lot of PDE people here, so let me formulate. Problem 2 can also be formulated as a pure PDE problem. Unfortunately, it's not not degenerate PDE, it's degenerate PDE. So, for example, okay, let's just write the PDE for in the C2 coordinates and use a ZW for the coordinate C2. You assume M is the graph of a real hypersurface in R3 here, the graph, okay, and let D be the positive curve side of M0. Suppose M hat is sitting above D, not this D0, sitting above D0, okay, and then M hat, so the graph is Levi-flat if and only if you can do the Levi determinant. Okay, so plotted that it's like a feminine matrix called the Levi determinant matrix. So this matrix, U alpha, U delta, U alpha delta, determinant. This equals to 0. This okay, is exactly this equation. It's exactly this equation. You see, it's a Monge-Bell type equation. But so here, because we have this term, we do not call it the Monge-Bell equation. We call the Levi equation. It's Levi equation. So it's a Levi equation. Okay. In higher dimension, the equation is more complicated. So I give you a reference here. It's, Tomasini is 1994. You know, so Levi is published in 1994. Okay. So the above equation called the Levi equation is degenerate. As I mentioned, there is a positive eigenvalue, but there is always zero eigenvalue. So there might be not PDE people, you know, but so a lot of people like these two guys, okay. But he is a complex analyst, very good complex analyst. Tomashini is more CR geometer, okay. And there are some other PDE people who I'm not familiar, but probably some of them. City, right? There's City, CITDI. He wrote many papers on this, okay. There are some other people, okay. So they prove that you use viscosity solution method. You can always find a solution which is C1 alpha, even not beyond C11. Okay, no more. And as I mentioned, no one has succeeded in getting any C2 solution so far. The reason is that why? Because once you have C2 solution, then the Fourierians start to jump out. Now, so the Fourierians jump out, then you really get this C-infinity solution. However, the Fourierian does not exist in general. So C2 solution does not exist, except in some very specialized complex geometric nice setting. What we call this setting. This is the only case you expect good solution. You can talk about the Levi equation here. You cannot get a solution. There is no solution. Okay, and so the non-PDE method never recognizes this geometric setting. So there's another very nice example. It's a Lamport, it's a green function. It's a Monge-Bell equation. Now that is a pure Monge-Bell equation. You study green function. He proved the regularity only for convex domain, and he did not do any estimate. So after Joe Paul, when you met him, he always tried to convince you to find the PDE proof. But this is not so. His proof is essential, right? He used extrudes, holomorphies. Okay, so it's very hard. One day there might be a PDE proof, but you have to find a method which recognizes the geometry, complex geometry. So now let's say a few words. So now Bishop discovered a very important geometry associated with M, so which makes the problem solvable. So neo in elliptic complex tangent point. Right? So he proved that there are not holomorphic beats attached to M. So what is holomorphic beats? So what he proved that there are not a map phi from unit disk delta to say Cn, and the boundary is attached to M. Phi is holomorphic, continuous on the boundary. Well, apparently, by using continuity method, the unit has to stay inside the hole. If there is an error solution, the image has to be on the graph. So this is the discovery of Bishop. Then he, at the time, he developed. So he, at the time, he was not able to solve the problem. He conjectured that what he discovered should be exactly what you need to solve all these problems. He said, there should be a lot more disks attached there, but actually, he said, you just take it. So here's Bishop conjecture essentially. Okay. So let me say it very briefly. What it means. So back to this lecture, I want so I'm a complex analyst. Okay. So now you're doing very class complex analysis here. So essentially, so Bishop said, you might have, so this is called an attached disk. Holomorph disk. So if the boundary is in M and F of course holomorphic, C0, continuous, okay? And so Bishop said, he found there are all of them, but he does not know, if these are all of them, okay? And he said, you take so all these disks, holomorph disks attached to, okay? He said, this is your whole, this is the solution to your plateau problem, whatever. Yeah, so this is what people call the Bishop conjecture, or Bishop problem, okay? And actually, he found a family of them. By solving this, what people call the Bishop equation. It's a singular integral equation, nonlinear volume, okay? And so he suspects that, he might have got all the disks. But, so in the 65, it's a long time ago. So it did not go further, okay? So this is remains to be a problem started by many people since his work. And Bishop's paper, as I mentioned, is the first paper dealing with manifolds with CR singularity. And so model from classical complex analysis, okay? And so let me say, many people, so Hunter, I don't know if this is the Hunter, so it's not your Bible, right? I didn't count it. The paper was 67.
No,
yeah. So then there's a Wells, so from Quran, and then these are 60s, and the 70s, these are 70s, and I need to Bedford wrote many papers here. And I only, because this is an important paper. Bedford, Gabor, Kenny Webster, most Webster, the 70s and 80s. And then in the 90s, so there's a personality goal, and so my journal is Crown and Koifman, etc. And the Bishop problem was finally solved in 1998. So now let's take the Bishop problem, okay? So the answer is yes. The answer is yes. So the answer is yes first. So suppose you are in the Bishop n-dimensional manifolds with an elliptical complex extending. Then there exists a smooth family of disjoint analytes with so attached is converting to B, whose unit amplitude is exactly the local holomorph of M mu, and it forms a smooth manifold, M+1 manifold, dimension manifold, such that M is contained in its boundary. Okay, and so most importantly, so any point there is only one disk attached to it, half the parameterization. So that's so moreover, if M is analytical, so then the equation, so the amplitude is also real analytic. So dimension 2, a complete solution due to Kenny Webster in the 82, and the higher dimension, so I did it in 98. Okay, so the crucial issue is full uniqueness of the attached disk and solve Bishop equation. So
in your case too, you have a singular integral equation, like the Hilbert transform.
Yeah.
Just the Hilbert transform or something?
No, it's a Hilbert transform along a curve. Yeah, so so it's like free boundary. You do not know which curve is your disk, right? If you know this, you extend the field. So you have to keep correcting it, So it's first you start from a very rough one. Because the boundary you do not know. If you know the boundary, then you extend it up, So
it's still one variable.
So it's one variable, but it's one variable. It's one variable because it's the critical dimension case. So it's there's only one complex variable jump in. If it's below dimension, it's completely real analysis. But now you see complex analysis here. It's all dimensional here with transform. So now, so in the 70s, so model observed many connections between the normal form theory for for B-sharp surfaces. For B-sharp surfaces, okay, with the problems from mechanics. And then he tried to approach the normal form after his work with Chen, okay. He started with he tried, okay, and he used the same approach what he used in the what he used with so to solve this he kind of use the same method to dealing with like the one I introduced to you, and then he obtained the following result. Okay, so what is the result? So this is the model result. He said so I can use the same method for which so he used with Chen to study CR geometry to get this pseudo-normal form. You can simplify. So this is the he tried the lambda equal to 0 case, but the lambda are bigger than 0 is the same. Okay, so this is the simplest for higher order invariant of M at a common extension point with a vanishing P-sharp invariant, which so we call the model invariant. So in this case, he solved the problem. He said if you formally you only get this model, then actually it's hypermorphic equivalent. So use the rapid convergent power theorems method. However, but this problem did not solve anything. However, the above pseudo-normal form is still subject to the action of the infinite dimensional group. Now I promise to tell you one example. Here's an example, okay? So C20, so we use normalized semi-normalization. You get the automorphism of the model. Now the model is still defined in our setting W equals this sphere. So the automorphism group you see here, these are two arbitrary functions. So the arbitrary function, the parallel coefficient could be arbitrary, but here you see, you only have many, just the coefficients here. So these two dimensions are exact the same. So what the function? So this does not solve any previous problem. Okay, what the function? Okay, so now, so it has been has been a very difficult problem to find what the function looks like. Okay, so it's not clear. So as I mentioned, there's another way. If you do not want to use this one group, then you really have to go to nonlinear decoupled systems, which I'm going to write down a little bit for you, okay? And so essentially you have some infinite many of equations simultaneously. And it's nonlinear, it's semi-linear. So first let's talk about the model vector theory. So model vector succeeds in the case when lambda is not equal to 0. But the other cases are not that interesting, but it's dynamic, okay? So model vector proves that, actually this function is just, so prove that. So here's a normal space. So you obtained by restricting to this group. So make the group smaller. And here is a normal space. And here, this is normal space. So this is normal space, okay? So and then this is the one group. Then another group is the whole group. You are supposed to use function this group, okay? Normalized group. This is the auto M model. And so you have to further simplify the stuff here by this group. In the Chen model case, I said, no worry, this group is too big, this is 5-dimensional. It's still good enough for you to make a lot of application you might imagine, okay? Model, okay? Now, in this setting, now these two groups have the exact same dimension, even larger in some sense. Okay? So model left group is 2.1. It's feminine, okay? This is model vector, okay? So you see, so forget about the other setting, because so just fix the utility case. That's what people care, okay? And so you see, this is a completely normal form. So lambda is B-sharp invariant, it's an invariant. X is invariant, epsilon is a sign, can only be 0, 1, negative 1. So this is regarded as half invariant. So there are two invariants. So this means when you further simplify further simplify the previous normal form, further simplify this one, by using this group, you are going to kill essentially all the coefficients. You only get 2.5 left there. But this 2.5 which left there are not just in some coefficients. It's scattered up. You know why? So this is this is what? It's an implicit normal form. You have the sum U. And then actually, so coefficient left there everywhere, but there are only 2.5 are independently. All the others are dependent on them. You know, so even now nobody succeeds to get an explicit norm form. You can solve from here, okay? So now let's say something, okay? So how model Webb did that? He did not try to use the normalization I introduced to you. He used it in induction. He found when lambda is not equal to 0, there is exactly, so there is a reduction. It's called a Moser-Webster triplet. And reduced to a problem in mechanics. And then he used what Beckhoff did, Seeger Beckhoff did, essentially. And get everything, and he found the one-to-one correspond, then he came back. So eventually, he avoided the difficulty here and reduced to problem in mechanics. And many problems, if you can solve direct here, you can apply this method to problem in mechanics. So this is model Webb thing. So this is an extremely deep paper, When you read the paper, so this is one paper I spent a lot more time to read than reading the model paper. Okay, it's because they use a lot of these Kramer mappings, so it's a seventh mechanical paper. When you read the paper, you find you're studying mechanics. That's your feeling.
So why are you saying 2.5? Because there is a U and Z and Z bar.
No, U is a U, no, U.
Yeah,
U,
no, why
U, so lambda is invariant. It's B sharp, okay? S is invariant. Okay, and the epsilon is only a sign. So when it's a sign, then for people doing invariant field, they call it half invariant. Okay, yeah. So and actually there's an integer invariant. It's very interesting. It's even less than 2.5. This is the real invariant. Okay, they have only 2.5 invariant. It's unbelievable. Okay, this quotient is only 2.5. So as this work is done, it's very natural to see because there's one case which is left. That's lambda equal to 0. Yeah. So now that's so in 83 and 85, Moser and Moser-Webb, so they ask, essentially, what's happening? So when lambda equal to 0, and their reduction does not work. So this reduction, you find is you have divided denominator by 0. So this means at the very beginning you are going to stop. Okay. The first question actually, so it's a special case of the B sharp problem. Okay. So so it's a flattening. Okay. So the flattening by special case. The B sharp problem is more for smooth category. Okay. Even Kenneth Webster, he did not solve B sharp problem in the real and big category. Okay. Real and big category is actually completely solved here. So that's a model problem. We solved the first problem, we solved it. Okay, 95. So this is analytic category. The second problem is about invariant theorem. So what I'm saying that when lambda equals to 0, the reduction does not work. Now, what about the normal space divided by something you need further to use to simplify? This is also bounded. It's also this is what people call the model problem. Okay, for the Bishop surfaces. Okay. So how to solve the equivalent problem here? And so this was actually in 1994, so when I went to Chicago as a teaching instructor, I started to think about this problem, So one day I came to Webster's office. He's a very nice guy, I said I found a geometry for this m equal to 0. I said if it's useful to solve this equivalent problem. So the geometry I found is that if you have m, let me say let's take a geometry. This is geometry. The geometry guide us for 10 years to find the solution of this problem. Okay. The geometry you have m equal to 0. And then you complexify this surface. So that, for example, it's w equal to z bar plus b z bar. Okay. And then you complexify. You replace this by the c new value. And this is the standard technique we use. And then, so this is also a defining equation. Okay. You replace w bar by eta. It's called the so you complexify. So here we are sitting in C2. And this idea is very important. Okay. This is C2. Okay. Now you look at a big surface here. This is the V W C eta C4. Defined by the complexification. It's called M. It's script M. Right? So this is the common surface. This is C2. Now I have a projection map. So any point ZW project down. Project down. So this is the covering map. It's a covering map. It's 1 to S covering map. It's 1 to S covering map. For a covering map. This covering map has branch locals. and it has exactly S range locals. And so surprisingly, all these range locals stay inside. So because I have theorem with currents, okay, so I can assume this is already sitting in a very nice place. You're sitting already in H. So then exactly. Let me draw a picture here. One, so suppose S equals 3. 3 of them sitting all inside M and cutting. So generically, they do not have the card. Okay, cutting, each disk attached to M. So cutting a disk into M. So now when you transform, normalize this M, okay, these branch lobes are invalid. The disk are invalid. So you get 2 set invalid. They cut 3 points. Okay, so essentially you get a disk with 3 points. So when you transform this M, the hyperbolic geometry decided by these 3 points are invariant. So now we try. So this is the question. Now when you try, so now what kind of normal form you expect? Now we are going to find there's like hyperbolic distance, angle, etc. They are very strange combinations. They are invariant. Okay. Now so we want to find the simplest form possible to make this for this invariant function. So when I ask the website, you think this is maybe now you're very close to solution. So as I mentioned, as I told you, okay. So when I met Chen, 95, in Houston, there was a conference for him in Houston. I was invited to give a lecture on the model wire tensor there. And then Chen told me actually, the story. He said, his contribution to that paper, that part, is he told Mozart, you should use this wire tensor geometry. And so that model so that kept in my mind for a long time. I asked Webster, okay. So he said this might be something which leads solution. But of course, you have a lot of technical detail you write up. There are a lot of things until we finish in 2009. So now the whole process is to find a nice representation for hyperbolic geometry here, so that this has a very good representation. That coordinates might be exactly the coordinates is sitting in the normal form. And this is the basic idea, and I think that's all the proof I can tell you. Okay. So eventually we solved this problem in 2009. Okay. So with my former student Yin, and so we showed that. So okay. So first part is a formal theory. We do not care about convergence. The second part we care about convergence. We said we said you can cancel two. So for example, let me just say it here. It's easier. So essentially, for example, s equal to 3. So we went to a very complicated. Eventually, we found so when you find a nice invariant function and you put the invariant function in the right condition, then you get this normal form. So this is a Mozart. With Mozart, so use the same method I introduced before. Okay. So this is the Mozart gap. It's very different from Chen-Model theorem. Chen-Model, you keep harmonic term. You want but here you only get harmonic terms, okay? But so actually the normal form. So this space you portion this group, and actually you kill which term? You kill this term, and your 2s you kill fourth term and the sixth term, okay? So what you get is that so this is what you get. And now this is a complete invariant. You can kill this term. It's very fortunate, so it looks very simple. For plus 3, 8. 80. So essentially, how many terms you kill? You kill 2/3. And you left 1/2. And then of course, when you transform to here, this A5 could be completely different. So then exactly take this form. And we did not, so you even don't know, so at the beginning, so what the normal form looks like. And eventually that's normal form you get. So you kill 2/3 of them. So this group is really big. You kill 2/3 of the previous, model pseudo normal form. Okay. And that's just, so the second part is about convergence. The convergence that, the convergence part is the convergence part is that so for everyone you put this in our normal form. M2 you also put in our normal form. Then these two our normal form may not be convergent. So however, but so if they share the same normal form here, if and only if essentially they are equivalent. Up to this multiplication, this is a very simple proof action, the S action, because of the S action. So if and only if the coefficients are proportional to each other. So that essentially solves the problem most and most Webster. Okay. So now you now setting here. So we solved in negative because both Mose and Webster and Mose they believe it should have finite. So but now in our situation, our infinity infinite infinity is not just 2.5. It's infinity again. Okay, so this infinity 1, infinity 2 is in general case is 2s is infinity. Okay, well this is not surprising. We know calculus. Okay, infinity by infinity could be anything, right? So sometimes you get final number. So this is the situation. So I still remember when I first told the website we got it. Okay, he said so it's finally infinity. I said infinity. I said I don't believe it. It's sure to be. Okay, and then eventually, so this is it's very surprising, So there's a huge difference for the normal form theory. For the analytic structure, homological plateau part, there's no difference at all. Because there's no difference at all. Because I mentioned that's my paper with the crowns. Okay, there's no difference at all. So that's there's no difference at all. So whenever they equal to 0, so that's the paper with crowns. When it's not equal to 0, it's already here. So it's all the analytic structure, okay? Now, so once you have normal form theory, so you want to see some geometric implication. There are many of them, but here I describe some of them. So let's say a few words, okay? A few words, okay? So most of Webster and Gong, so since of Webster, we did a lot of things about normalization here. And there are many hyperbolic, if we go beyond elliptic, which have the same normal form, but they are never converged to each other. It's very interesting problem dynamics to find the module space, okay? So our conversion argument different from what used by most Webster here, reduced to problem of majority method, and most of Gong and Storm, which are using a lot of small divisor. And so different from what used by CR setting, by people like Bawendi, Appenfeld, Rothschild, Samir. So here I think that in this area, the best expert is this guy. Okay, he did a very deep thing. Okay, but this is it's an excellent application of what people call Artin approximation. So it's a pure algebraic geometry problem for the huge application here. Yeah. So Artin approximation. Okay. So now so let's give some so our argument is, as I mentioned, is based on the flattening theorem of my result with crowns and the hyperbolic geometry I just described. Everything is from that. This tiny little geometry, you try to manipulate with the function from here, and then every time you get a little bit better information there, you normalize a little bit. Then you make the function here better, you normalize it. So don't try to directly solve the equation. It's unsolvable. It cannot do it. So it's beyond the reach of human brain. Okay, it's unidimensional. So many. I give a unidimensional system. Just arbitrary equation, and there is no way you understand here. You really have to use geometry. Think about it. So where you go, the road. Just you want to go to Himalaya, right? You have to tell me the way to go. Otherwise, how could I be there? I even get lost. Where is west, where is north? Yeah. So so the geometry guiding us is this hyperbolic geometry, a little bit of geometry. Okay, what I do? Now, so what are the consequences now? So infinitely many dimensions, infinitely many invariants. There's too many invariants, okay? And everything here is invariant. A5, and there are also absolute invariants. So it's not like the model. You just multiply. So infinitely many invariants. So this is exactly what I'm saying. Now it's infinity, okay? And generic or non-algebraic. So this is most of us they think so in their setting what they did is that you have a series, you keep truncating, and somewhere you don't have to truncate anymore. They found that the truncating are the same. Okay. So now what does that mean? When you have a series you truncate it, this means it's algebraic. It's equivalent to algebraic. But here we prove here now there's So this is the general framework for boundary array. So there's so many beautiful stuff about this invariant field, you know. So I already have a book on this, you know. So so there's a wavelength not theory. It's another fundamental idea of boundary. People have been using for years, even after boundary died 100 years. Okay, still using this idea. Here there's another idea of boundary. So what is the idea of boundary? So boundary said, okay, if I have some object. And so I want to see, you know, for example, if I have a manifold, I want to see if it's algebraic. Now, so boundary said, okay, algebraic, okay, it's algebraic, so because degree 1, I only have one dimension, so I have a dimensional space. 2, I only have 2, and so the margin space and 2, dimension 3, because the defining function right now, so the space of dimension cannot be infinite. And algebraic means you unit them up. You unit them up. So this means what? If everybody here is algebraic, then this means this space are the same. But the issue is that here it's always a Fechel space, complete Fechel space. And this is the first Bell category. How could it be the same? Cannot be the same. So this means generically speaking, this means this space is nowhere dense field. That's what I mean generically algebraic. So this is not my idea, okay? So this is the boundary, okay? But so once you know, so this is the immediate consequence. So it's genetic non-algebraic. This means, you know, genetics, give you a service, you rotate a little bit, you truncate, cannot be the same as the previous one. Don't truncate it. You have to do it even in many steps. Okay. And then another interesting application, you know, it's about the automorphism group. So you look at this. There's a model here. It's a pseudo model. It's not this model. So the automorphism group is always a subgroup of this guy. It's always a subgroup of ZX. So the automorphism group is always subgroup of ZX. And actually, the automorphism group of the M equal to ZX if and only if it's a model. So it's like a uniformization in this setting. Well, I would like to compare this with the famous Wang-Rosé, and actually it's called Wang theorem. Okay, Rosé would be really upset if I put Wang-Rosé. But anyhow, so people the SCV start to use Wang-Rosé. So it's Wang theorem, which says in a strong convex type surface. So any group, the automorphism group is a subgroup of the ball. If the automorphism group is the same as the group of the ball, then it's hypernormal of the ball. So here it's the same here. So after saying all this, it means essentially, when lambda equal to 0, it behaves like a strong pseudo-coherence manifold. It's not so essentially. It's although dimension is 2, but actually behave like dimension 3 star. Yeah, there are more. Okay. So I think probably so I 15 minutes. I want to hurry up. So let's forget about the Cartesian theory. Okay. It's in my lecture notes. Okay. Yeah, look at my Chima lecture notes. I have like 30-page discussion. Well, that's another beautiful theory. I really want to discuss. I remember in Chima I talked for 3 weeks. Okay. I have all this time to went through the whole thing. But you give me 5 lectures, I can have 1 more to tell you Cartesian theory. Yeah, but anyhow, so I feel very sorry. I think probably it's more useful for you. But I thought I have to tell you. So I'm a complex analyst. Because I'm telling something about something in CN. Cartesian theory is a pure geometry. There's nothing with CR geometry. I can talk about 15 more if you like that.
You cannot say Cartesian theory is not anything to do with CR.
Well, of course, it has application. No, what I'm going to do is I'm doing the general different geometry. Then eventually I give application.
That's a statement.
I think probably I just stop here. So thank you so much. I really appreciate the invitation. I enjoyed very much my stay here.